The universe is a massive place filled with countless wonders and mysteries. And within this vast expanse, our own planet drifts as a small, steady world of familiar rhythms. From distant galaxies filled with uncountable stars to the quiet darkness that surrounds our solar system, space stretches beyond what we can fully understand. And yet, in the middle of this immensity, Earth turns calmly on its axis, carrying all of life as we know it through the silent night. Far above the surface, if we could watch from the stillness of space, we would see Earth as a softly glowing sphere, wrapped in thin layers of air and cloud, slowly rotating beneath a sky crowded with stars. Continents and oceans slide gently from day into night and back again, as the planet spins eastward at more than 1,035 miles per hour at the equator, a motion so smooth and constant that we rarely notice it at all. The sun appears to rise in the east and set in the west, not because the universe moves around us, but because this turning world quietly shapes our sense of time. This rotation is a source of order and energy, a simple spin that guides every sunrise and sunset, every tide pulled by the moon, and every breath of wind that crosses the surface of the oceans and continents. In these ways, the daily turning of our planet helps organize weather systems, ocean currents, and the patterns of climate that allow forests, deserts, and cities to exist where they do. It is a testament to the dynamic and transformative processes of the cosmos that such a basic motion can influence so much of what we experience on Earth. Yet, in a universe where planets, stars, and galaxies follow many different paths, we can pause to ask a quiet question. What if, over long spans of time, our planet spins slowly reversed until Earth turned the other way and the familiar rhythm of day and night began to run backward across the sky? The sun would seem to rise in the west and sink in the east. Star trails would curve in the opposite direction, and the invisible forces that guide winds and currents would be gently but profoundly rearranged. Join us as we embark on a journey into this reversed world, not as a tale of sudden catastrophe, but as a calm, guided exploration of physics, climate, oceans, and human history. We will move unhurriedly from the grand scale of gravity and planetary motion down to the most intimate details of daily life, tracing how a backward spinning Earth would reshape storms, seasons, and the places we call home. As we travel through this thought experiment, you are invited to simply imagine and visualize, letting each scene unfold at its own pace, like a slow rotation beneath the stars, as we explore the wonders of the cosmos through the subtle change of a single planetary spin. To understand how a single change in Earth's spin could ripple through everything we experience, we first need to look calmly at how the rotation we live with now shapes the world we know. Join us as we embark on a journey not across the galaxies this time, but around our own planet, turning once every 24 hours beneath the light of our star. Earth's rotation, a steady spin from west to east, completes one full turn in roughly a day, with the equator racing through space at about 1,038 miles per hour, while the poles simply pivot in place. From tiny particles of air to vast ocean basins, everything on the surface shares this motion, and because of it, we see the sun, moon, and stars appear to rise in the east and drift westward, even though it is our planet that is turning under the sky. From our quiet vantage point, this simple spin becomes the grand clock that organizes life as we know it. The day-night cycle is the most familiar expression of this motion, a direct and elegant consequence of rotation. As Earth turns, each location on the surface is carried from darkness into sunlight and then back again, producing the rhythm of sunrise, noon, sunset, and midnight that we build our lives around. The boundary between day and night, a moving line called the terminator, sweeps across continents and oceans like a slow wave of shadow and light, setting the pace for sleep, work, migration, and the daily flow of energy through ecosystems. Yet rotation does more than simply turn the lights on and off. It gently bends the paths of moving air and water through a phenomenon known as the Coriolis effect. Because different latitudes spin at slightly different speeds, air that tries to move straight from high pressure to low pressure is subtly deflected, curving to the right in the northern hemisphere and to the left in the southern hemisphere. In these ways, trade winds are steered toward the tropics, jet streams snake high above us, and vast storms spin counterclockwise to the north and clockwise to the south, a testament to the dynamic and transformative processes of the cosmos acting on a planetary scale. This same turning influences many patterns we take for granted, from the graceful arcs of long-distance flights that curve over the poles, to ocean currents such as the Gulf Stream that carry warm water toward Europe and help moderate its climate. Even long-range artillery and rockets must quietly account for Earth's rotation, aiming not at where a target is now, but where it will be after the planet has turned beneath their trajectory. When we recognize how deeply this eastward spin is woven into weather, navigation, and the flow of heat across our world, we become better prepared to imagine what would happen if that spin were reversed, and the entire system of winds, currents, and familiar directions slowly turned the other way. The universe is a massive place filled with countless wonders and mysteries. Yet some of the most intricate patterns we encounter unfold right here, in the thin shell of air and water wrapped around our spinning planet. From tiny swirls of dust to vast bands of clouds stretching across continents, Earth's rotation quietly choreographs a hidden web of motion that shapes the conditions for life as we know it. The Coriolis effect, a subtle consequence of our turning world, is at the heart of this choreography. Because the surface near the equator moves eastward faster than the higher latitudes, air that tries to flow straight is gently deflected, curving to the right in the northern hemisphere and to the left in the southern hemisphere. In these ways, simple pressure differences blossom into organized wind belts, steady trade winds blowing from the subtropics toward the equator, and prevailing westerlies flowing from the subtropics toward the poles, each guided by the planet's rotation. These great rivers of air, in turn, push on the oceans, transferring momentum and energy into the water, and setting immense currents into motion. The result is a set of vast gyres, rotating basins of flow in each ocean, which carry warm water from the equator toward higher latitudes and return cooler water back toward the tropics. The Gulf Stream in the Atlantic, the Kuroshio Current in the Pacific, and their counterparts around the globe act as planetary conveyor belts, smoothing temperature contrasts and helping to stabilize regional climates over long periods of time. Storm systems also organize themselves around this rotational framework, revealing how deeply gravity, pressure, and spin are intertwined. Mid-latitude cyclones that sweep across North America and Europe spiral counterclockwise in the north, while their southern hemisphere analogues turn clockwise, all because Coriolis nudges inflowing air into rotation. Tropical hurricanes and typhoons drawing heat from warm ocean surfaces follow the same rule. Their rotating cloud shields and clear eyes, a testament to the dynamic and transformative processes of the cosmos expressed on a planetary scale. We experience the consequences of this invisible structure in very familiar ways. Typical storm tracks arch from west to east across the United States and Canada, then continue toward Europe, bringing sequences of rain, snow, and clear skies that many of us take for granted. In Asia, the seasonal reversal of winds, guided by the same global circulation, powers the monsoons that deliver life-sustaining rains to India, Southeast Asia, and parts of China. From relatively stable seasons in temperate zones to the dependable timing of wet and dry periods in the tropics, our calendars, agriculture, and cities are all quietly tuned to this rotating pattern. Join us as we embark on a journey of imagination and physics, and a gentle question emerges. If this entire interconnected web of winds, currents, and spinning storms depends on the direction of Earth's rotation, what new patterns would arise and which familiar ones would fade if the planet's spin slowly turned the other way? To follow that question, we first need to place a gentle boundary around our imagination, because not every scenario the universe allows us to picture is one that physics would easily permit. The Earth, as a rotating planet, carries an immense reservoir of angular momentum, a stored form of motion and energy bound up in its daily spin. And changing that motion is far more demanding than it might appear from the quiet turning of the sky. Right now, our planet rotates eastward at roughly 1,038 miles per hour at the equator. And this steady spin defines our 24-hour day, the path of the sun across the sky, and the invisible Coriolis forces that guide winds and currents. To reverse that spin, we would need to first bring this enormous rotation to a complete halt, and then accelerate the entire Earth in the opposite direction, an undertaking that would require an amount of energy comparable to unbinding and rebuilding the spinning world itself. In these ways, the scale of the problem already tells us that a sudden flip is not just unlikely, but physically extreme. No known natural process in our solar system could gently provide such a reversal. A collision large enough to stop and restart Earth's rotation would be far more violent than the giant impact that once helped form our moon. And instead of leaving behind oceans and continents, it would almost certainly melt the crust, boil the seas, and strip away much of the atmosphere that supports life as we know it. The quiet pattern of days and nights, seasons and storms would be replaced by a molten, glowing sphere, a testament to the dynamic and transformative processes of the cosmos when gravity and energy act without restraint. Because of this, when scientists explore a backward-spinning Earth, they do not imagine a catastrophic blow from space arriving without warning. Instead, they turn to computer models, to equations that already describe winds, clouds, and ocean currents, and they simply change the sign of the rotation term as if the planet had always turned the other way. In numerical form, the Coriolis effect that bends storms and shapes jet streams is reversed, and the simulated atmosphere and oceans are allowed to adjust gradually, step by step. Join us as we embark on a journey into that controlled, alternate Earth, not as a disaster movie, but as a calm thought experiment, a world that formed rotating westward from the beginning, orbiting the same sun under the same gravity, with the same continents and oceans initially in place. This framing lets us explore the wonders of the cosmos expressed through climate and habitability, asking how deserts, rainforests, and currents might rearrange themselves without dwelling on apocalyptic impacts. From this safer vantage point, we can now watch how winds reorganize, how oceans reverse their great highways of heat, and how the conditions for life might subtly shift on a planet that looks familiar, yet turns the other way. From this safer vantage point, we can imagine not just maps of wind and water, but the sky itself quietly rearranging its patterns above us. Join us as we embark on a journey into a single imagined morning, when the familiar rhythm of Earth's rotation has been reversed, yet the world still appears calm enough for us to notice details rather than disasters. We begin in a quiet bedroom, somewhere in the mid-latitudes as first light seeps through the curtains. The glow feels ordinary at first, a soft brightening of the world. But when we step to the window and look out, there is a subtle disorientation. The horizon to the west, where we usually watch sunsets fade behind distant clouds, is now brightening instead. And the sun, our local star and source of almost all the energy that drives weather and life as we know it, lifts itself gently above a landscape that has never seen dawn from that direction. As we walk outside, the air is cool and still, and the familiar landmarks of our town or city seem unchanged, yet the motion of light over them is reversed. Shadows stretch toward the east, long and delicate, pointing away from the rising sun, and as hours pass, we would watch that sun trace its path from west to east, crossing the sky in the opposite direction before descending toward an eastern evening. In these ways, the passage of time would feel slightly unfamiliar, as if the day were running along an invisible track laid out backwards. Over many days and nights, the difference would become even clearer when we looked up after dark. The stars, those distant suns scattered across the universe, would still form the same constellations, but their slow drift from one horizon to the other would be mirrored. Long exposure photographs, which once captured graceful circular star trails turning one way around the celestial poles, would now record arcs sweeping the other way, a quiet visual record that the entire planet is rotating in reverse beneath the galaxies overhead. Our inherited habits of navigation would have grown up differently on such a world. Sailors learning to cross oceans and travelers mapping early trade routes would never have spoken of the sun rising in the east, and simple sayings used to teach direction would have been built around western dawns and eastern twilights instead. Compasses would still point along lines of magnetic force, but maps, mnemonics, and even childhood drawings of the solar system would have encoded a sky that appears to turn the other way, a testament to the dynamic and transformative processes of the cosmos written into culture. Standing under this reversed sky, with dawns in the west and familiar constellations gliding the wrong way, we might start to wonder what else has changed. If the heavens above us feel mirrored, what deeper, invisible systems beneath that sky are also quietly turning the wrong way, reshaping oceans, climates, and perhaps the future paths of life itself? On a world where the sky itself seems to run in reverse, our entire practice of watching the heavens would quietly rearrange itself, even though the deeper mechanics of the universe would not change at all. The same galaxies would shine, the same stars would burn, but the way they glide overhead each night would tell a different story. Join us as we embark on a journey into this mirrored observatory, where timekeeping, tracking, and the familiar rhythms of the sky are all gently inverted. The apparent daily motion of the heavens, the slow sweep of stars, planets, and the pale band of the Milky Way from one horizon to the other is set first and foremost by Earth's rotation. Today, because our planet spins eastward, we see the sky drift from east to west, and we mark that motion in sidereal time, measuring how long it takes a star to return to the same point overhead. Reverse the spin, and this grand rotation would reverse as well. So constellations would appear to rise in the west and set in the east, and long exposure star trails around the celestial poles would curl in the opposite direction. Observatories, those careful eyes of our species, would adapt to this retrograde world with mirrored habits. A telescope on an equatorial mount, which now tracks stars by slowly turning westward to match the sky's drift, would instead turn the other way, its gears and motors designed to compensate for a sky that slides eastward. The tracking software that predicts where planets and comets will appear would use the same equations grounded in the same gravity and orbital mechanics, but with signs flipped in its rotational terms, a quiet mathematical reflection of the changed spin. Timekeeping, too, would feel different while remaining anchored to the same physics. A sidereal day defined by one full rotation relative to the distant stars would keep essentially the same length, because Earth's spin rate has not changed, only its direction. A solar day defined by the sun's return to local noon would still be close to 24 hours, but local noon would now be when the sun reaches its highest point in the southern sky after rising in the west and crossing toward the east. In these ways, our clocks and calendars would be recalibrated, yet the orbits of planets around the sun and the formation of seasons would continue as before, a testament to the dynamic and transformative processes of the cosmos that lie beneath surface appearances. Even satellites circling our planet under the same laws of motion would present a subtly altered dance to observers on the ground. A low Earth orbit satellite that moves west to east relative to the stars today would still follow that path in space. But because the ground beneath now turns the other way, its ground track would bend differently across the continents, and its apparent arc from horizon to horizon would trace a new pattern across the reversed sky. From X-ray observatories to weather satellites, the infrastructure of observation would adjust its pointing and timing, yet still harvest the same streams of energy and information from space. From this reversed dance of the heavens, where every star trail and satellite pass is mirrored, we are naturally led downward to the air and water that also feel Earth's turning. As the rotation flips, so too do the great currents of atmosphere and ocean, and in the next part of our journey we will watch the winds, storms, and currents reorganize themselves, reshaping climate, ecosystems, and perhaps the future of life as we know it beneath this backward-turning sky. To understand how a reversed Earth would reshape weather and water, we first need to pause with the planet we know and trace the quiet machinery of its present-day climate. From the equator to the poles, our atmosphere behaves like a vast heat engine, moving energy from regions that receive more sunlight to regions that receive less, and in these ways smoothing the extremes that would otherwise challenge life as we know it. Near the equator, where the sun's rays strike most directly, the surface warms strongly and the air above it becomes hot, humid, and buoyant. This air rises in towering columns, forming the belt of frequent thunderstorms and deep clouds that we associate with the tropical rainforests. As it ascends, it spreads poleward high in the atmosphere, gradually cooling, losing moisture, and eventually sinking again in the subtropics, roughly around 30 degrees north and south, where broad zones of high pressure are established. This circulation pattern rising at the equator and sinking in the subtropics is known as the Hadley cell, and it is the first of 3 interconnected cells in each hemisphere. Beyond it, in the mid-latitudes where many of us live, lies the Ferrel cell, a more complex indirect circulation that helps guide the prevailing westerly winds and the familiar parade of low-pressure systems. Closer to the poles, cold, dense air sinks and then flows equatorward at the surface, forming the polar cell and the polar easterlies that rim the icy caps. Together, these 3 cells per hemisphere shaped by Earth's rotation and the Coriolis effect generate the major wind belts that encircle our planet. Trade winds blow from the subtropics toward the equator, curving westward. Mid-latitude westerlies sweep from west to east, steering storm systems over oceans and continents, and polar easterlies complete the pattern. Join us as we embark on a journey through this invisible framework, which quietly orders clouds, storms, and seasons. Where air sinks and dries in the descending branches of the Hadley cells, we find many of the world's great deserts, a testament to the dynamic and transformative processes of the cosmos playing out on a planetary scale. Around 30 degrees latitude under persistent high pressure lie the Sahara and Arabian deserts, the deserts of Australia, and the dry zones of northern Mexico and the southwestern United States. Farther poleward, under the influence of the Ferrel cell and the mid-latitude westerlies, we encounter stormy, temperate regions with frequent frontal systems and strong jet streams. These broad patterns connect directly to places we recognize on a map. The storm tracks that sweep across the North Atlantic, for example, are guided by the westerlies, delivering rain and wind to eastern North America and western Europe. Over South and East Asia, the seasonal shifting of pressure systems and winds creates the monsoons, whose alternating wet and dry phases support dense populations and intricate ecosystems. From the Amazon basin to the Indian subcontinent, this climate engine underlies agriculture, water resources, and the rhythms of daily life. Now, as we hold this familiar arrangement in our minds, a planet with deserts near 30 degrees, storm belts in the mid-latitudes, and tropical rains straddling the equator, we are ready for a pattern interrupt. What happens if we reverse the direction of rotation, asking the same sun to rise in the west and set in the east? In the next part of our journey, we will take this map of climate belts and, under a different spin, watch it slide, twist, and reform into a surprisingly altered world. When we reverse the spin of an entire planet, we are not just changing where the sun appears to rise. We are reaching into the invisible machinery of the atmosphere and turning its gears the other way. Join us as we embark on a journey into this flipped engine of air, where the familiar patterns of wind and weather are gently but profoundly rewritten. On a rotating world, every large-scale motion of air feels the subtle tug of the Coriolis effect, a consequence of Earth's spin and the changing linear speed from equator to poles. In our present configuration, air moving in the northern hemisphere is deflected to the right of its path, while in the southern hemisphere it is deflected to the left, helping to set up the spiraling structure of storms and the broad bands of wind that encircle the globe. If Earth were to spin backwards, this mathematical sign would simply invert, so that every moving parcel of air would now curve in the opposite direction, a quiet but far-reaching reversal of the forces that guide our weather. From the equator to the mid-latitudes, this change in curvature would reshape the great atmospheric conveyor belts that carry heat and moisture. Today, the trade winds blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, converging along the equator and feeding towering clouds and tropical rains. Under a retrograde spin, these trades would reverse, arriving from the northwest and southwest instead, still converging, but now drawing their air from very different source regions and ocean surfaces. In these ways, the pathways by which warm, humid air is delivered to the tropics would be redrawn, altering the timing and intensity of monsoons and shifting the zones where deep convective storms routinely form. Farther poleward, in the belts where many of us live, the mid-latitude westerlies that now blow from west to east would become easterlies, flowing from east to west and carrying weather systems in the opposite direction. The jet streams, those narrow, fast rivers of air high in the atmosphere that trace the boundaries between warm and cold air masses, would also flip their direction and subtly adjust their meandering paths over the continents and oceans. Storm tracks that currently guide low-pressure systems across North America, Europe, and Asia would be rerouted, so that regions accustomed to frequent frontal passages and rapidly changing conditions might find themselves under calmer, more persistent skies, while other coastlines and interior basins could be visited again and again by recurring cyclones. In practical terms, this means that a city that now lies on the stormy downstream side of an ocean basin could, in a reversed world, sit on the more tranquil upstream side, while formerly sheltered regions might experience an almost conveyor-like delivery of powerful systems. Over decades and centuries, these reorganized winds would not only reshape daily weather, but also the deeper climate patterns that determine which landscapes become deserts and which evolve into rainforests. Climate simulations of a backward spinning Earth suggest that vast dry regions like the Sahara could green and support dense vegetation, while parts of the Americas might dry and expand into arid belts, a testament to the dynamic and transformative processes of the cosmos, even on a single rotating planet. As we move forward, we will see how the oceans, responding to this new pattern of winds, would carry heat and nutrients along entirely different routes, completing the transformation of our world's surface. The atmosphere of a backward spinning Earth would not only reshape deserts and rainforests, it would also rewrite the very architecture of storms. From gentle trade winds to the most violent cyclones, the invisible influence of rotation would quietly but profoundly redirect the flow of energy around our planet. A small reminder that even here, far from distant galaxies and stars, the laws that sculpt the universe are always at work. Today, tropical cyclones, which we call hurricanes or typhoons, depending on where they form, arise from a familiar sequence of events. Warm ocean water heats the air above it, that moist air rises and cools, and towering clouds of thunderstorms blossom, releasing latent heat and feeding further uplift. The Earth's rotation then adds a subtle twist. The Coriolis effect, a consequence of our spinning planet, nudges these sprawling storm clusters into rotation, organizing chaos into a coherent, spiraling engine that can stretch hundreds of kilometers across. On our present Earth, this organization follows a simple rule. In the northern hemisphere, cyclones spin counterclockwise, while in the southern hemisphere, they turn clockwise, a pattern that has become so routine that meteorologists, pilots, and even students intuitively expect it. This preferred direction is not a property of the storms themselves, but of the rotating frame in which they live, a testament to the dynamic and transformative processes of the cosmos, acting on scales as small as a raindrop and as large as a planetary atmosphere. If we reverse the spin of the Earth, we reverse that frame. The Coriolis effect would flip sign, and with it, the handedness of every large-scale vortex. On a retrograde world, northern hemisphere cyclones would spin clockwise, and southern hemisphere storms would swirl counterclockwise, their cloud shields still elegant and spiral-shaped, but curling in the opposite direction. Join us as we embark on a journey of imagination in which every satellite image we have ever learned to read would appear subtly but unmistakably wrong. The changes would not stop at spin. The background winds that guide storms, from the trade winds that blow near the surface to the high, fast jet streams, would also reverse. And in these ways, the highways that steer hurricanes across the oceans would be redrawn. Storms that now recurve away from certain coasts might instead be funneled toward them, while long familiar hotspots of cyclone landfall could find themselves in relative calm, their risk exported to regions that, in our history, never faced such regular impacts. Over centuries, this alternate pattern would seep into culture and memory. Sailors' lore, traditional stories about storm seasons, and the earliest weather maps in this parallel meteorology would all be built around clockwise spinning tempests in the north and opposite swirling systems in the south. Our intuitive sense of how the sky behaves, from the direction of cloud bands to the tilt of storm fronts, would have grown up entirely reversed, yet would feel just as natural, just as inevitable, to the people living beneath those clouds. As we contemplate this mirror image planet where winds, rains, and cyclones all dance to an inverted rhythm, we are led to a deeper question. If the atmosphere responds so completely to a simple change in spin, what happens to the far larger, slower, and more massive circulations that wrap the globe? In the next step of our journey, we will follow that question into the oceans themselves and watch as the great currents of water that help sustain life as we know it are turned back upon their paths. To understand what happens when we turn the planet's spin back on itself, we first need to see how the oceans move now, under the quiet guidance of winds and rotation. Join us as we embark on a journey across the surface of the seas, where invisible forces carve vast highways of flowing water that help sustain life as we know it. On our present Earth, the atmosphere and the oceans are linked in a single, rotating system, and the same rotation that shapes the jet streams also sculpts the surface currents. The trade winds, steady bands of easterly winds that blow toward the equator, and the westerlies, stronger winds that sweep the mid-latitudes, push on the ocean's skin, and over time this transfer of energy gathers water into enormous rotating gyres in each major ocean basin. From tiny ripples near the coast to broad, slow swirls spanning thousands of kilometers, the Coriolis effect bends these flows, turning straight wind-pushed paths into graceful spirals that circle the basins like vast, liquid galaxies. Within these gyres, distinct currents emerge, each with its own character and climate story. The Gulf Stream, a powerful western boundary current in the North Atlantic, carries warm, salty water from the tropics toward higher latitudes, releasing heat into the atmosphere and softening the winters of Western Europe far beyond what its latitude alone would suggest. On the other side of the planet, the Kuroshio Current plays a similar role off East Asia, transporting tropical warmth toward Japan and helping to shape the storm tracks that sweep the North Pacific. Encircling Antarctica, the Antarctic Circumpolar Current, the largest current on Earth, flows unbroken around the globe, connecting the Atlantic, Indian and Pacific basins and redistributing heat, salt and nutrients between them in a continuous band. Beneath these swift surface rivers, a slower and deeper system works on timescales that rival the ages of civilizations. This is the thermohaline circulation, the global conveyor belt driven by differences in temperature and salinity, where cold, dense water sinks in the high latitudes of the North Atlantic and around Antarctica, then creeps through the deep ocean before rising again in distant upwelling regions. In these ways, surface and deep currents together move heat from the equator toward the poles and return cooler waters toward the tropics, a testament to the dynamic and transformative processes of the cosmos playing out on our own planet. These flows are not abstract. They shape regional climates and ecosystems that we depend on. The Gulf Stream's warmth contributes to the mild, damp winters of places like the United Kingdom and Norway, while along the western coasts of continents, cold eastern boundary currents such as the California Current bring chilled water equatorward, fostering foggy coasts and temperate summers. Where winds pull surface waters away from shore, deeper, nutrient-rich water rises to replace them, fueling immense blooms of microscopic life and supporting major fisheries off Peru, Namibia, and California. The arrangement of deserts, forests, and productive coastal seas is tied, in part, to where these ocean highways run today. Now we introduce a quiet but profound pattern. Interrupt. If we reverse the direction of Earth's spin, the winds that drive these currents would reorganize, and the Coriolis effect would change sign. The trade winds and westerlies would shift, the gyres would reverse their rotation, and the familiar paths of the Gulf Stream and Kuroshio would be redrawn or even replaced, as if the ocean's map of invisible roads had been erased and traced anew. In the next stage of our exploration, we will follow these altered winds and currents to see how entire coastlines, climates, and ecosystems might be transformed when the planet's great heat transport system begins to run in reverse. The oceans, which already act as vast conveyors of heat and energy around our rotating world, would respond to a backward spin with a quiet but radical reorganization. From the surface waters that brush familiar coastlines to the deep currents that circle entire basins, the invisible highways of the sea would be redirected, and with them, the climates of continents. On our present Earth, the trade winds and westerlies, guided by rotation and the Coriolis effect, help twist the great ocean gyres into their current shapes, driving clockwise circulation in the northern hemispheric basins and counterclockwise in the southern ones. Reverse the spin, reverse the winds, and those immense gyres would flip their direction, sending warm and cold currents along entirely different coastal routes, as if the planet had drawn a new set of climate borders on the same map of land. In the North Atlantic, this becomes especially striking. Today, the Gulf Stream, a powerful warm current, carries tropical heat northeastward toward Western Europe, softening winters and supporting a mild maritime climate that is unusually gentle for those latitudes. In a retrograde Earth scenario, climate simulations suggest that an analogue of this current might instead hug the eastern coasts of North America, directing warm water and moist air toward regions that are now more continental and seasonally extreme, while Europe will be left exposed to colder, more polar-influenced waters and air masses. From tiny coastal ecosystems to entire weather systems, the consequences would cascade. Eastern North America could feel more like a buffered, ocean-tempered realm, while Western Europe might experience sharper seasonal contrasts, more severe winter cold, and altered storm tracks, a testament to the dynamic and transformative processes of the cosmos, playing out not among distant galaxies, but in our own planetary seas. In these ways, a simple reversal of spin would rearrange which shores benefit from the ocean's stored solar energy, and which are left in the path of chillier flows. Upwelling zones, the regions where deep, cold, nutrient-rich waters rise to the surface, would also be reshaped. Today, persistent winds along the western edges of continents, interacting with rotation, pull surface waters away from the coast and allow nutrient-laden water to well up, supporting rich fisheries off places like Peru, California, and Northwest Africa. With the winds reversed and the Coriolis deflection flipped, many of these productive zones could weaken or vanish, while new upwelling systems might emerge along what are currently quieter, nutrient-poor coasts, redistributing marine life and human livelihoods alike. Climate models that explore this backwards spinning Earth show that sea surface temperatures would change in complex, basin-wide patterns, altering where storms draw their moisture and energy, shifting rainfall belts and even moving the boundaries of seasonal sea ice. Join us as we embark on a journey into these simulations, where the reconfigured currents and winds do something especially surprising. They help transform the Sahara into a green, rain-fed landscape, while parts of the Americas dry and fade into desert. How does a simple change in rotation turn familiar regions into their climatic opposites? In these simulations, scientists take our familiar planet and change just one fundamental property. They reverse the direction of Earth's spin while leaving the continents, the tilt of the axis, and the amount of sunlight exactly the same, creating a controlled experiment on a planetary scale. From tiny eddies in the atmosphere to global bands of wind and rain, the entire circulation adjusts to this new sense of rotation, revealing how deeply the daily turning of our world shapes climate, weather, and the possibilities for life as we know it. When modelers run these global climate codes, they see the trade winds and jet streams, which are guided by the Coriolis effect, flip direction, and with them, the great conveyor belts of moisture that feed our deserts and forests. Join us as we embark on a journey into one of the most striking results. In a backwards spinning Earth, the Sahara, which today is the largest hot desert on the planet, becomes a sprawling green zone, its sands replaced by savannas, wetlands, and dense tropical vegetation. Moist air, redirected by the reversed circulation, is driven inland from the Atlantic, and monsoon systems that are weak or absent today blossom into powerful, regular, rainy seasons. In this retrograde world, North Africa is no longer a barrier of heat and dust, but a vast corridor of rivers and lakes, a testament to the dynamic and transformative processes of the cosmos, even on a single planet. The models show rainfall totals increasing dramatically, with conditions more reminiscent of the Amazon basin or Southeast Asia than of the present-day Sahara. From the Atlantic coast deep into the interior, clouds would build each year. Thunderstorms would march across the landscape, and ecosystems rich in biodiversity could take root where only sparse drought-adapted species survive now. Yet this greening of one region is balanced by drying elsewhere, as the redirected flow of energy and moisture leaves some lands in the rain shadow of the new circulation. In many simulations, the eastern parts of North and South America, which today enjoy relatively wet climates, shift toward aridity, as the reverse trade winds carry moisture away rather than toward the continents. Areas that now support dense forests, fertile farmland, and major rivers begin to resemble the semi-arid plateaus and deserts of our current world, with shorter wet seasons, weaker storms, and soils that struggle to store water from one year to the next. Asia, too, undergoes a profound reorganization as the monsoon systems that depend on seasonal heating and large-scale wind patterns are reshaped by the retrograde spin. Some regions that currently rely on steady summer rains would see those rains intensify, with stronger, more focused monsoon bursts, while others, especially on the opposite flanks of mountain ranges, would dry, losing the dependable downpours that sustain agriculture and dense human populations. In these ways, the habitable belts of the Eastern Hemisphere slide and twist across the map, and the familiar outline of where large civilizations can thrive becomes almost unrecognizable. From green North African plains to parched American heartlands, the overarching lesson from these models is quietly astonishing. By changing only the direction of rotation, without moving a single continent or altering the sun's output, we migrate entire climate zones across the surface of the globe. The deserts, grasslands, and rainforests that define our current geography are revealed as temporary patterns in a fluid system governed by rotation, gravity, and sunlight. And the apparent stability of our homeworld becomes just one configuration among many possible Earths. As we continue, we can explore what such a reversal would mean not only for temperature and rainfall, but for the oceans themselves, where currents like a reversed Gulf Stream would redraw the thermal map of the planet and further transform the environments that galaxies of living organisms call home. The atmosphere, like the oceans, does not simply accept a reversed Earth. It reorganizes itself, tracing out new, invisible rivers in the sky. Join us as we embark on a journey into these shifting winds, where familiar monsoons dissolve and reform in unexpected places, and the boundaries between wet forests and dry deserts slide across the continents. Today, monsoons, those vast seasonal breathing patterns of the atmosphere, arise because land and ocean do not warm and cool at the same rate. In summer, continents heat rapidly, air rises, and lower pressure over land draws in moist air from the surrounding seas, feeding towering clouds and months of rain. In winter, the pattern reverses, land cools, high pressure develops, and dry winds flow seaward, bringing clear skies and drought. From India to West Africa to northern Australia, these oscillations between wet and dry seasons sustain agriculture, rivers, and life as we know it. On a retrograde Earth, the fundamental contrast between land and ocean remains, but the background flow in which these monsoons are embedded is turned around. The trade winds, which today blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, would reverse, and the jet streams, those high-altitude bands of fast-moving air, would bend in the opposite sense around the planet. In these ways, the same heating patterns would now interact with a different conveyor of air, changing where moisture-laden winds can be drawn inland and where they are pushed away. Climate simulations of a backward-spinning Earth suggest that India, which currently receives its life-giving summer monsoon from the southwest, might instead find its strongest moist inflow redirected along a different path, or shifted in timing, with rainfall arriving in new months or focusing on different coasts. Southeast Asia, today wrapped in warm, humid air from surrounding tropical seas, could see altered monsoon corridors, moving heavy rains toward what are now comparatively drier interiors. West Africa, whose monsoon now pulls Atlantic moisture deep into the continent, might lose that direct connection, while new monsoonal surges could rise from an altered Atlantic or even from a transformed Mediterranean, reorganizing where savannas, wetlands, and dry Sahel-like zones can form. The great desert belts of the world are also tied to the global circulation. Subtropical high-pressure zones, descending branches of the Hadley cells, currently anchor regions like the Sahara, the Arabian Peninsula, the Australian interior, and parts of the Americas in persistent dryness. Reverse the spin, and these high-pressure centers, guided by different jets and trades, would migrate in latitude and longitude, shifting the core of aridity onto new continental targets. In some simulations, the Sahara becomes green, while deserts expand across what is now the Amazon basin and the southeastern United States, a testament to the dynamic and transformative processes of the cosmos playing out on a planetary scale. If the winds and pressure belts redraw the map of rain and drought, then forests, grasslands, coral reefs, and entire chains of ecosystems must either move, adapt, or vanish. As we continue, we can explore how this reversed climate engine would reshape the biosphere itself and ask which forms of life could follow the changing rivers in the sky and which would be left behind. The universe of living things on Earth is woven from climate, and climate, in turn, is woven from rotation. When the spin reverses, the familiar patterns of wind and water that feed forests, grasslands, and deserts are redrawn, and with them, the entire map of life as we know it. Join us as we embark on a journey across this retrograde planet, where the sky turns the other way and ecosystems must learn to follow. On our present Earth, temperature, rainfall, and the rhythm of the seasons set the boundaries between biomes, from humid jungles to frozen tundra, all guided by the way energy flows from equator to poles and is shuffled by winds and currents. On a backwards spinning world, the trade winds and jet streams bend in the opposite directions, monsoons strike different coasts, and the great storm tracks shift. So the same continents host entirely new combinations of heat and moisture. From this altered circulation, new climate zones emerge, and ecosystems either migrate with them or fade. Tropical rainforests, which depend on year-round warmth and abundant rain, would follow the new belts of rising rain-laden air that encircle the retrograde Earth. Climate simulations suggest that regions like North Africa, today dominated by the vast Sahara, could fall beneath a persistent convergence of moist winds, turning into a broad green band of dense forest and swamp, threaded with great rivers and cloud towers. At the same time, parts of the Amazon basin or Southeast Asia could dry. Their current storms diverted elsewhere, forcing the jungle canopy to retreat upslope or poleward, leaving behind mosaics of seasonal woodland and savanna. The fate of the deserts would be just as dramatic, a testament to the dynamic and transformative processes of the cosmos expressed on a single planet. Where sinking dry air is displaced, sand seas may bloom into grasslands, with former dune fields anchored by roots and shaded by scattered trees. The Sahara could fragment into savannas and closed canopy forests, while new desert belts might establish themselves over interiors of the Americas, Europe, or Eastern Asia, where reversed winds strip away moisture before it can fall. Regions that now sustain dense agriculture could find themselves under clear, relentlessly dry skies. Migratory species from songbirds and cranes to butterflies, dragonflies, and great herds of hoofed mammals would trace these moving climate corridors like living instruments measuring the new flow of energy across the globe. Ancient flyways that once followed coastlines, river valleys, and prevailing winds would bend or vanish, replaced by new aerial highways linking the greened North Africa to Eurasia, or connecting emerging grasslands on one continent to fresh feeding grounds on another. Some species would adapt by shifting their routes and timing. Others, unable to bridge the new gaps between breeding and wintering grounds, would decline or disappear. In these ways, the land would reorganize into a different but still intricate tapestry of forests, steppes, wetlands, and deserts, all keyed to a reversed sky. Yet the story does not end at the shoreline. If winds and rainfall can drag whole biomes across the continents, then the ocean currents driven by those same forces must also change, and with them, the invisible frontiers that separate warm and cold waters, rich fisheries, and marine deserts. As we move from the coasts into the global ocean, we can ask how coral reefs, plankton blooms, and migratory whales respond when the planetary conveyor belts beneath the waves begin to run in reverse. Across the surface of this reversed world, the reshaped winds and currents would not only redirect heat, they would reorder the very seas of life. Join us as we embark on a journey beneath the waves, where invisible flows of energy and nutrients quietly determine which coasts teem with fish and which remain blue deserts, almost empty despite the vastness of the ocean. Many of the richest fisheries on our present Earth are anchored to a subtle process called upwelling, where winds push surface waters aside and deep, cold, nutrient-rich water rises from below. From the coasts of Peru and California to the waters off northwest Africa, this upwelling fuels immense blooms of phytoplankton, the microscopic plants of the sea. And in these ways it supports anchovies, sardines, tuna, seabirds, and whales, building entire food webs from a thin, green veil of life at the surface. If we reverse the spin of the planet, the trade winds and mid-latitude westerlies also reverse, and with them, the geometry of upwelling and sinking. Regions that are now biological engines, like the Humboldt Current along South America, could weaken or vanish as winds pull water in the opposite direction, while new upwelling zones might appear along coasts that are currently far less productive. Familiar fisheries would falter or collapse, and new hotspots of abundance would emerge, perhaps along eastern shores of the Americas or different reaches of Asia, a testament to the dynamic and transformative processes of the cosmos acting even within a single planet's oceans. From tiny plankton to vast coral reefs, the distribution of marine life is written in temperature, chemistry, and light. Coral reefs, which thrive in clear, warm, but not overheated tropical waters, depend on the routing of warm and cold currents around the continents. A reversed Atlantic with a Gulf Stream flowing the other way might no longer bathe the Caribbean and parts of Europe in the same patterns of heat, stressing existing reefs with unfamiliar temperatures, while creating new refuges in places that are now too cool or too variable for reef formation. In these ways, belts of coral might retreat from some equatorial regions and expand into subtropical zones, redrawing the map of underwater cities where countless species feed, hide, and reproduce. The great migration routes that connect oceans, from whales following plankton blooms to tuna tracing sharp fronts between warm and cold water, would slowly realign with the new corridors of productivity, as if the invisible highways of the seas had been lifted and carefully laid down in different places. Here we meet a quiet pattern interrupt. This reversal of spin would not only redirect currents and clouds, it would also have rewritten our entire human story. For as long as we have watched the skies and sailed the oceans, we have used winds, stars, and tides to navigate, to define sacred directions, and to build myths about the structure of the universe itself. A sun rising in the west, a different arrangement of storms and coasts and altered marine routes would have changed where early civilizations flourished, how trade networks formed, and even how religions imagined the order of creation. As we leave these transformed seas behind, we can now turn to the broader ways a backward-spinning Earth would reshape human history, culture, and our understanding of life as we know it. Human history, like climate, is not fixed. It is a pattern written in rainfall, rivers, and the slow turning of our world beneath the sky. On a backward-spinning Earth, the same continents and the same species would exist, yet the stories we tell, the cities we build, and the paths we walk across the surface would be profoundly rearranged. Join us as we embark on a journey through this alternate timeline, where a simple reversal of rotation reshapes life as we know it. From North Africa to South Asia, the band of deserts and monsoon lands that guided early human migrations would be shifted and transformed. Climate simulations of a retrograde planet suggest that the Sahara, which in our history became a vast barrier of sand, could instead be a green, rain-fed landscape, threaded with lakes, savannas, and dense river networks. In such a world, early agriculture might take root not only in the Fertile Crescent, but across a broad, habitable corridor stretching from a lush Maghreb into what is now arid Arabia, turning today's marginal oases into cradles of dense settlement and early cities. When we follow the water, we begin to see how different river systems, nourished by altered winds and storm tracks, would favor new centers of civilization. Monsoons redirected by reversed trade winds could deliver heavier rains to the western flanks of continents, swelling rivers that are minor in our history, and diminishing some of the great waterways we depend on today. The Nile, the Tigris and Euphrates, and the Indus might share their civilizational spotlight with now quiet basins in North Africa or Western Australia, while interior plateaus in the Americas, deprived of moisture, could remain sparsely populated, a testament to the dynamic and transformative processes of the cosmos acting through climate and gravity on human choices. Trade, which links distant cultures into a single planetary web, would trace very different paths along coasts and oceans governed by reversed winds and currents. with the great gyres of the oceans spinning the other way, and with storm belts displaced, the easiest sailing routes might run from Western Africa towards the Americas, and from Western Europe toward a colder, drier Atlantic fringe, elevating ports that are minor today into major hubs of commerce and exploration. In these ways, the map of influential maritime powers could tilt toward different nations and shorelines, changing which languages, technologies, and ideas spread most efficiently around our world. Even our inner worlds, our mythologies and symbolic geographies would be recast beneath a sky where the sun always rises in the west and sets in the east. Dawn emerging over western horizons might be linked with ancestral realms or oceans instead of with the promise of the east, while the eastward dusk could become a direction of endings and uncertainty. Sacred architectures might face west to greet first light, and epic journeys could be described as moving from sunset toward sunrise, in reverse of our narratives, embedding the planet's retrograde spin into every ritual and story. Under such a sky, our tools for finding our way would feel subtly altered as well. Compasses would still seek magnetic north, yet the habitual association of east with sunrise and west with sunset would be inverted on every map. And star lore would describe constellations that appear to wheel across the heavens in the opposite direction. As we look ahead, we can explore how, on this reversed Earth, these changes in orientation would influence science, navigation, and our broader understanding of our place in the universe. On a retrograde Earth, the simple act of knowing which way to go would unfold under a sky that moves in the opposite direction, and our entire history of finding our way across land and sea would have taken shape along very different lines. Join us as we embark on a journey into this mirrored world of directions, where familiar rules still obey the same physics, yet their meanings drift into new territory. Magnetic compasses, those quiet tools that align themselves with Earth's magnetic field, would still dutifully point toward the magnetic poles, because magnetism is tied to the planet's core and not to the direction of spin. North would still be north in a physical sense, and south would still be south. Yet the deep cultural bond between east, west, sunrise, and sunset would have been reversed from the dawn of navigation. From the earliest maps scratched into clay to the first carefully inked charts of oceans and continents, cartographers would have drawn their symbols and legends around a sun that rises in the west and sinks in the east, and the very idea of orienting a map would have grown from a different reference. For ancient seafarers who once watched the familiar constellations rise in the east and arc westward, the sky on this backward spinning planet would tell its stories in reverse. Star paths would still be precise, regular and reliable, but Orion, the Big Dipper, and the band of the Milky Way would appear to lift themselves from the western horizon and drift eastward through the night. So traditional wayfinding techniques would have developed as mirror images of those we know. Polynesian navigators, desert caravans, and Arctic hunters would all have learned to follow these reversed celestial tracks, and their star lore passed down through generations would describe the heavens as a great wheel turning the other way, a testament to the dynamic and transformative processes of the cosmos. Modern navigation, shaped by engines, satellites, and global trade, would also be reconfigured by this opposite spin, because the same rotation that defines day and night also sculpts winds and currents through the Coriolis effect. On our present Earth, prevailing trade winds, jet streams, and great ocean currents like the Gulf Stream help determine efficient aviation and shipping routes, guiding aircraft along high-altitude rivers of air and vessels along powerful surface flows. On a retrograde Earth, those patterns would be flipped. Jet streams would tend to run in the opposite sense. Storm systems would spiral the other way, and major currents would reorganize, so airlines would schedule their long-haul flights to ride west-rising tailwinds, and cargo ships would trace new corridors along reversed ocean highways. Even the simplest teaching phrases, the small verbal tools we give to children as they first learn about the world, would be different. The sentence, "The sun rises in the east," would never be coined. Instead, school books would quietly state that dawn comes from the west, and entire languages might embed the west as the direction of beginnings and the east as the realm of endings. In these ways, the vocabulary of direction, the metaphors in literature, and the symbolism in art and religion would all align themselves with this opposite daily motion of the sky. Yet navigation is only one layer of our relationship with Earth's rotation, and deeper still lie our systems of timekeeping, calendars, and daily rhythms, all calibrated to the turning of our planet beneath the stars. If the sky has always moved the other way, how far would that difference reach into our sense of past and future, our rituals, and even our experience of life as we know it? In the next part of our exploration, we will follow this reversed spin into the clocks on our walls, the festivals in our year, and the hidden ways a backward sky might reshape human culture across the ages. To understand how deeply a backward spin would touch our sense of time, we first need to remember what would stay the same. The length of the day, set by how long Earth takes to complete one rotation, would still be about 24 hours, and the length of the year, set by our orbit around the Sun, would still trace out the same path through space. What changes is the direction in which we watch the sky move overhead. In our present world, the Sun, a medium-sized star at the heart of our solar system, appears to rise in the east and set in the west, because Earth turns eastward, carrying us into and then out of the sun's light. On a reversed Earth, the same rotation speed and the same flow of energy from the sun would remain, but the sun would climb from the western horizon and sink in the east, and the stars would seem to wheel across the sky in the opposite sense, rewriting the visual rhythm that early observers used to anchor their calendars. Many of the first calendars were not abstract systems, but careful records of when certain stars rose just before dawn, or when the sun reached particular points along the horizon. Join us as we embark on a journey into that alternate history. In a world where dawn belongs to the west, sacred mountains and city gates might have been aligned toward that glowing edge of the sky. And the direction we now call west could instead have carried the symbolism of awakening, renewal, and the beginning of tasks and journeys. In these ways, religious and cultural rituals that mark sunrise and sunset would be quietly rotated across the landscape. Imagine morning prayers, now offered while facing west toward the first light, or evening ceremonies oriented toward the east as the last rays fade, shaping temple courtyards, burial grounds, and processional roads. From ancient stone circles to later cathedrals and mosques, the geometry of sacred architecture would follow the path of the west-rising sun, embedding this reversed motion of the heavens into the daily experience of life as we know it. Artistic and literary traditions would follow. Today, Many cultures associate the East with beginnings and the West with endings, so that journeys towards the West often suggest decline, rest, or death, while the rising sun in the East stands for hope and progress. On a backward spinning Earth, those metaphors might invert. Stories could send heroes toward the West in search of new possibilities, while the East might come to represent closure, memory, or the quietness of completion, a testament to the dynamic and transformative processes of the cosmos acting through human imagination. Then, as we trace these imagined rituals and symbols, we can pause for a pattern interrupt and step back into the underlying physics. Beneath calendars and cathedrals, beneath myths and metaphors, the simple fact of rotation, set by angular momentum as Earth formed from a spinning cloud of gas and dust, would still govern what is possible, shaping tides, guiding the flow of the oceans, and linking our cultural sense of time to the deeper machinery of the universe. The universe is a massive place filled with countless wonders and mysteries, yet even something as familiar as the turning of our own world is rooted in the same deep laws that guide galaxies and stars. Join us as we embark on a journey back to the very beginning of the solar system, to see how Earth first learned to spin. The story starts inside a vast, cold molecular cloud, a drifting region of gas and dust spread over light years, where gravity slowly gathers material into denser clumps. This cloud, enriched by earlier generations of stars, already carried a slight overall rotation, a gentle swirl almost imperceptible on human scales, but crucial for what followed. As a portion of the cloud collapsed under its own gravity, conservation of angular momentum, the rule that spin cannot simply disappear, forced that slow turn to quicken, flattening the material into a rotating disk around a growing proto-star that would become our sun. From tiny grains of dust to mountain-sized planetesimals, matter in this spinning disk collided, stuck together, and shattered again in a long, chaotic process of accretion. Each impact transferred a little angular momentum, nudging young planets to spin faster or slower and tilting their axes one way or another, yet the overall direction of rotation was largely inherited from the original disk. In these ways, the simple fact that the disk turned in one preferred direction led most of the emerging worlds to turn the same way. Today, most planets in our solar system rotate in the same direction that they orbit the Sun, a motion we call prograde, so that if we look down from above the Sun's North Pole, they all move counterclockwise together. There are striking exceptions that reveal how violent the early solar system could be. Venus turns so slowly and in the opposite, retrograde direction that its day is longer than its year, while Uranus is tipped on its side, rolling along like a spinning ball, a testament to the dynamic and transformative processes of the cosmos and to titanic impacts in its youth. Earth's own eastward rotation, carrying the surface at about 1,670 kilometers per hour at the equator, is simply one historical outcome of this turbulent formation, not an inevitable rule of physics. Under slightly different initial conditions, with different collisions and tilts, our planet could have ended up turning westward instead, giving us sunsets where we now see dawn, while still sustaining life as we know it under a different sky. Even without reversing direction, Earth's spin is not fixed forever. Tidal interactions with the moon steadily transfer rotational energy outward, lengthening our day by tiny fractions of a second each century. In the next section, we will see how this changing directional spin shapes winds, oceans, and climates, and what might unfold if that ancient choice of direction were somehow reversed. The universe is not only vast in space, but also in time, and over these immense ages, even something as steady as a day on Earth slowly changes under the quiet pull of gravity. Join us as we embark on a journey into the subtle partnership between our planet and its moon. A partnership that has been reshaping Earth's rotation since the very beginning. The moon, a rocky companion world orbiting just over 380,000 kilometers away, raises tides not only in our oceans but also, very slightly, in Earth's crust itself. As Earth spins beneath this gravitational influence, the great tidal bulges of water and rock do not sit exactly beneath the moon. Friction between the moving oceans and the sea floor drags these bulges a little ahead of the moon's position in the sky. In these ways, the daily rise and fall of the seas that we experience along our coasts are part of a much larger exchange of energy and motion between two worlds. Those forward-shifted bulges act like gravitational handles, and they tug back on the moon, exerting a torque that transfers angular momentum from Earth's rotation into the moon's orbit. The result is elegantly simple. Earth's spin gradually slows, and the moon very slowly spirals outward, its orbital distance increasing by a few centimeters each year. What we feel as the rhythm of tides is, on a deeper level, a testament to the dynamic and transformative processes of the cosmos, where even apparently stable systems are always evolving. Over hundreds of millions of years, this tidal breaking has had measurable consequences. Geological and fossil evidence from ancient coral growth rings and tidal sediment layers indicates that hundreds of millions of years ago, days on Earth were several hours shorter, with perhaps 21 or 22 hours of daylight and darkness combined instead of the 24 we know now. The length of the day continues to increase by milliseconds per century, an almost imperceptible effect to a single human lifetime, yet one that accumulates across epochs as continents drift, oceans reshape, and life as we know it adapts to a slowly lengthening cycle of light and dark. Crucially, this tidal interaction always acts in the same sense. It resists motion and drains rotational energy, forever slowing but never reversing the direction of spin. To actually flip Earth's rotation so that the sun would rise in the west, an unimaginably large external torque would be required, perhaps from a catastrophic impact with a Mars-sized body or a sustained gravitational encounter far beyond anything present in our solar system today. If such a force did act, trying to wrench our planet into spinning backwards, what would happen to the crust, the oceans, and the fragile web of life clinging to the surface? In the next section, we will explore how such a reversal would reshape winds, currents, and climates across the globe. To understand what a reversed Earth might mean, we first need to pause at the edge of an even more dramatic possibility, one that we will not fully enter. The Earth, a rotating planet bound together by gravity and internal strength, carries an enormous store of kinetic energy in its daily spin, and any attempt to stop or suddenly reverse that motion would unleash consequences far beyond the scale of familiar storms, quakes, or impacts. At the equator, our planet's surface moves eastward at about 1,670 kilometers per hour, and when we calculate the rotational energy of the entire Earth, we arrive at a value on the order of 10 to the 29th power joules, a number so large that it is difficult to visualize. From tiny particles to massive galaxies, the universe is filled with energy. Yet this single reservoir of spin rivals the output of millions of large nuclear weapons detonated every second for days. And in these ways, it reminds us how deeply rotation is woven into the structure of our world. To cancel that energy abruptly would not be like applying a gentle brake. It would be like asking the whole planet to absorb a blow from a cosmic hammer. If the solid crust were forced to a halt while the oceans and atmosphere tried to keep moving, inertia would rule the next moments. Vast walls of water would surge over continents as global mega-tsunamis, racing eastward with the speed inherited from the former rotation, while the air itself would become a scouring wind, in many places likely reaching or exceeding the speed of sound. Cities, forests, and coastlines would not simply experience bad weather, they would be swept by the momentum of entire ocean basins and atmospheric layers, trying to continue their path through space. Beneath our feet, the story would be no calmer. The tectonic plates, which usually drift at the pace of fingernail growth, would suddenly find themselves dragged, twisted, or sheared against the underlying mantle, that slowly convecting layer of rock that behaves like a very viscous fluid over geological timescales. Mountain ranges could experience stresses far beyond those that raised them. Faults might rupture in sequence around the globe, and magma systems could be disturbed into widespread volcanic activity, a testament to the dynamic and transformative processes of the cosmos playing out within a single planet. Fortunately, such an abrupt reversal is not something scientists regard as a realistic threat. There is no known process in our solar system that could deliver the required impulse without first destroying the Earth entirely, and no hidden mechanism inside the planet waiting to flip its spin overnight. We explore it only to appreciate the immense scale of rotational energy, and to see why any sudden change would be catastrophic for life as we know it. So, instead of imagining a violent, impossible jolt, we will take a quieter path. For the rest of our journey, we will picture an Earth that has always spun backwards, from its earliest cloud of dust to the present day, allowing continents, climates, and ecosystems to adapt as they formed. Join us as we embark on a journey across this mirror world, where the sun rises in the west, the winds and currents flow in unfamiliar directions, and the first subtle clues of a reversed rotation begin to reshape the face of the planet. From the very beginning, an Earth that spun backwards would have written a different story into its rocks, its oceans, and its skies, even though it orbited the same sun in the same universe. The same gravity would shape the same continents and basins, yet the flow of air and water over those young surfaces would trace new patterns, leaving a quiet but permanent record of a reversed rotation. On our Earth, the newborn oceans and atmosphere began to circulate under an eastward spin, setting up familiar trade winds, storm tracks, and equatorial currents that carved humid belts and dry zones into the first stable crust. On a retrograde Earth, those winds would still arise from uneven solar heating, but the Coriolis effect would bend them the other way, reshaping the great bands of climate that circle the globe. In these ways, early tropical rain belts might favor the opposite sides of the emerging continents, while coastal upwelling zones, nutrient-rich and cool, would appear where today we see warm, clear subtropical waters. As time passed and the planet's orbit continued to cycle through subtle variations in tilt and shape, ice ages would still come and go, driven by the same orbital mechanics that govern our own glacial eras. Yet the places that froze and the regions that dried into desert would be shifted, sometimes dramatically, by the altered winds and currents. Vast ice sheets might advance more readily across western rather than eastern continental margins, while interior basins that are arid in our history could become corridors of lakes and wetlands, a testament to the dynamic and transformative processes of the cosmos, acting through something as simple as spin. Supercontinents like Pangaea, assembling and breaking apart under deep tectonic forces, would also feel this difference. Mountain ranges, which already steer storms and cast rain shadows, would now interact with reversed prevailing winds, sending moist air up one flank instead of the other, and relocating long-lived deserts by thousands of kilometers. Inland seas could expand where persistent onshore winds drive moisture and river inflow, while other basins deprived of reversed monsoons might never fill. The geology would look familiar in outline, yet the distribution of ancient dunes, coal swamps, and evaporate deposits would tell an alternate tale. These climatic rearrangements would guide where early life concentrated and where the chemical archives of that life accumulated. Extensive coal deposits, which on our Earth formed in humid, low-latitude wetlands, might cluster along different continental margins, while major oil-bearing basins could shift to coasts favoured by long-lived upwelling and oxygen-poor bottom waters. Future civilizations, rising much later under alien star patterns that still belong to the same galaxies, would discover their richest fuels and minerals in unfamiliar places, building their first cities and trade routes along coasts that, in our history, remained comparatively poor. And then, as we leap forward into a technological age on this backward spinning world, the consequences would reach beyond geology into the infrastructure of a global society. Preferred aviation routes would arc differently across the map. Satellites would trace mirrored ground tracks as the planet turned beneath them, and launch sites would migrate to coasts where the reversed rotation still lends a subtle boost of energy to rockets climbing toward orbit. Join us as we embark on a journey from this deep time mirror back to the present moment, where we can finally ask how such a world would feel to live on day by day, under a sun that always rises in the west, on a world where dawn comes from the west and the familiar rhythm of the sky has been gently inverted. The invisible rivers of air that circle the planet would also be transformed, and with them, the way we cross the globe. The universe may seem remote when we speak of galaxies and stars, yet here, in the thin blue shell of our atmosphere, we find a quieter reflection of those vast dynamics, written in winds, pressure, and motion. Modern aviation is already deeply entwined with these high-altitude patterns. The jet streams, fast-moving bands of wind that meander through the upper troposphere and lower stratosphere, act as aerial conveyor belts that aircraft can join or avoid, trading time and fuel for careful navigation along these currents. From North America to Europe, for example, we routinely fly eastward within a strong tailwind, shortening overnight flights across the Atlantic, while westbound journeys push against that same flow and arrive more slowly. If Earth's rotation reversed, the broad structure of the atmosphere would remain, but the dominant directions of these jets would flip, because the Coriolis effect that steers them is tied to the direction of planetary spin. The familiar mid-latitude jet streams that now flow predominantly from west to east would over time reorganize into powerful east-to-west bands, so the very routes that currently enjoy helpful tailwinds would instead face persistent headwinds, and the traditionally slower directions would become the fast lanes of the sky. In these ways, the map of optimal routes between major cities would gradually be redrawn. Flights from New York to London, which today descend into the sunrise with strong assistance from the jet, would be lengthened and fuel-hungry, while westbound returns would be brisk, riding the reversed flow back toward North America. Paths between Tokyo and Los Angeles, between São Paulo and Johannesburg, and along many Great Circle arcs would be recalculated to weave through regions of favorable wind, even if that meant more pronounced curves on a flat map. A quiet testament to the dynamic and transformative processes of the cosmos acting on our daily lives. Over decades, airlines would shift refueling hubs and emergency diversion airports to better align with these new corridors of efficient travel, clustering infrastructure where tailwinds are most reliable and where strong crosswinds are less likely to close runways. Air traffic control patterns would adapt as well, with holding stacks, approach paths, and even the preferred directions of takeoff and landing slowly reoriented around prevailing winds that differ from those on our real Earth. And some airports might eventually rebuild or add runways to match the altered climate of the skies above them. Just as aircraft quietly harvest the energy of these atmospheric rivers, our spacecraft harvest the planet's rotation itself, using launch sites and trajectories that lean on Earth's spin to reach orbit. Join us as we embark on a journey beyond the clouds, where a backwards-turning world would not only reshape our flights through the air, but also change the very pathways by which we rise from this planet into space. From the surface, a backwards-turning Earth would change the rhythm of our days and the paths of our winds. But as we rise beyond the clouds, another subtle consequence appears in the way we leave the planet at all. Rockets do not simply fight gravity with raw power, they lean on the motion of the world beneath them, quietly borrowing some of the planet's rotational energy to climb into orbit more efficiently. Today, Earth spins eastward, and that eastward motion is fastest at the equator, where the surface races along at about 1,670 kilometers per hour. When we launch a rocket eastward from a site close to the equator, such as the European spaceport at Kourou in French Guiana, that rotational speed adds directly to the rocket's own velocity. In these ways, the planet itself gives us a head start, reducing the amount of fuel required to reach the speeds needed to circle Earth or to escape into the wider solar system. This is why so many major launch sites are placed at low to mid-latitudes with open ocean to the east. Cape Canaveral in Florida, Baikonur in Kazakhstan, and Kourou all take advantage of the eastward spin, sending most rockets over water for safety and into orbits that align naturally with the direction in which Earth travels around the Sun. The result is a global launch infrastructure that is, in a quiet but very real sense, built around the present direction of our planet's rotation and its place within the solar system. On a retrograde Earth spinning westward instead, the free boost would point the other way, and our launch strategies would slowly but profoundly reorganize. To place spacecraft into prograde orbits around the Sun, still following the overall direction of the planets and the flow of the solar system, we would likely prefer westward launches from near the equator. Spaceports might cluster along coasts where open ocean lies to the west rather than the east, and regions that are today peripheral to spaceflight could become central, a testament to the dynamic and transformative processes of the cosmos, acting even on our engineering decisions. As the direction of rotation reversed, the patterns traced by satellites across the sky would also adjust, their ground tracks sweeping over continents in mirrored arcs, and the coverage of weather, communication, and navigation constellations would be redesigned to match. Global navigation systems would still guide ships and aircraft, but their orbital planes, repeat cycles, and timing would be tuned to a westward spinning world, embedding the new rotation into the infrastructure of life as we know it. From orbit, however, the backwards Earth would look both familiar and quietly strange. Continents and oceans would lie where we expect, yet cloud bands, storm spirals, and ocean currents would unwind in reversed swirls, like a reflection of our world seen in a cosmic mirror. Join us as we embark on a journey from these mirrored patterns in low Earth orbit to the broader wonders of the cosmos, where even a single planet's spin is only one note in a much larger celestial symphony. From this mirrored Earth turning quietly below, we can lift our viewpoint even higher until we are drifting in a silent spacecraft, suspended in the darkness, watching the entire planet rotate like a slow, luminous globe. Join us as we embark on a journey above the clouds, where the familiar rhythm of our world is preserved in length and speed, but its direction and our intuition about it has been gently reversed. In orbit, the first difference would be subtle yet profound. The continents and oceans still glide past beneath us in a steady 24-hour cycle, but instead of sliding from west to east under our path, they drift from east to west. The Earth, a spinning planet shaped by gravity and ancient formation processes, now turns backwards under our spacecraft, so that the bright limb of sunrise creeps towards the west, and the line of sunset pursues it from behind, tracing a path that feels like the replay of a film in reverse. As we watch, bands of cloud begin to tell the story of this retrograde rotation. The long, sweeping trade wind clouds that we usually see angling from east to west across the tropics now lean the other way, their streaks drawn out along reversed wind belts. Vast storm systems, those spiraling expressions of atmospheric energy, curl in opposite directions compared to the animations we know, with northern storms winding clockwise and southern storms unwinding counterclockwise, a quiet inversion of the Coriolis patterns we take for granted. The large-scale features of the climate engine are still there, yet each one carries the signature of a world that spins the other way. The intertropical convergence zone, that bright equatorial band of towering cloud where trade winds collide and rise, still rings the planet, but its subtle tilts and seasonal meanders trace mirrored arcs across the oceans and continents. Mid-latitude storm tracks still snake around the globe, but they march along altered paths, guiding cyclones and rain belts into regions that, on our present Earth, are much drier. Even the great ocean gyres, those slow, basin-spanning whirlpools that steer currents like the Gulf Stream and Kuroshio, now swirl in the opposite sense, redistributing heat and nutrients along coastlines that would experience very different conditions for life as we know it. If we compress hours into seconds, a time-lapse of day and night sweeping across this backwards world becomes a mesmerizing band of shadow and light. The Terminator, that moving boundary between day and darkness, slides around the globe in the opposite direction, so the sun appears to rise in the west and set in the east, and the dance of city lights switching on and off unfolds in a pattern that our instincts struggle to read. In these ways, even simple satellite loops and global weather animations would need to be relearned, their arrows, swirls, and flows all pointing against our expectations. From this serene vantage point, surrounded by the quiet wonders of the cosmos and the steady glow of distant stars and galaxies, it is easy to be lulled by the elegance of reversed clouds and mirrored currents. Yet far below, beneath that shifting veil of cloud and the turning line of day and night, lie power grids, cities and fields, all bound to this new pattern of winds and waves, and the true challenge of how our infrastructure adapts to a backwards spinning Earth is only just beginning to unfold. From the scale of continents and oceans, we now descend into the fine mesh of human systems, where wires, roads, and crop rows trace out our response to climate and light. Join us as we embark on a journey across this reversed Earth, where the same physics of rotation and energy still rule, yet the patterns that support our cities and fields have been quietly rearranged. Modern power grids, vast invisible networks of cables and transformers, are built around the rhythm of demand that follows weather and season. In cold northern winters, we draw heavily on heating, in hot subtropical summers on cooling, and in storm-prone regions we harden lines and substations against wind, ice, and lightning. On a backward spinning planet, the jet streams, storm tracks, and monsoon systems that guide these needs would migrate, so the peaks and lulls of electricity use would shift with them, forcing us to rebalance where we generate power and how we move it across continents. Renewable energy, which depends so directly on the atmosphere and oceans, would feel this transformation even more strongly. Regions that today rely on steady trade winds or predictable mid-latitude westerlies might find those winds weakened, redirected, or arriving in different seasons, altering the reliability of vast wind farms and the economics of the grid. Hydropower, which turns falling water into usable energy, would track the new rainfall belts. A basin that once enjoyed regular snowpack and spring melt could dry under descending air, while former deserts, now under rising, moisture-laden currents, might host new rivers, dams and reservoirs, a testament to the dynamic and transformative processes of the cosmos, even here on Earth. Agriculture would migrate with these climate belts following temperature, rainfall, and the timing of the seasons, much as it has throughout history, but now on a global, mirrored scale. Wheat, which thrives in temperate, moderately dry zones, might retreat from parts of North America and Eurasia and instead spread across regions that become the new, grain-friendly corridors on this reversed world. Rice, which demands warmth and abundant water, would anchor itself along the shifted monsoon arcs, while maize would fill in the transitional climates between, reshaping the map of food production and the sea lanes and rail lines that carry harvests between continents, altering global trade as thoroughly as if new galaxies of commerce had appeared. Cities, those dense nodes of stone, glass, and light, would also respond to the redirected winds and waters. Coastal megacities, now accustomed to certain prevailing storm paths and sea level patterns, could find themselves facing surges from unfamiliar directions, with waves amplified by altered currents and tides. Some would raise new sea walls and storm barriers. Some would redesign drainage, transport, and building codes, and others, especially in low-lying deltas or subsiding coasts, might slowly relocate inland, their skylines dissolving and reforming like clouds under changing gravity. For each of us, this backward spinning Earth would be felt most intimately in the quiet details of a single day. The sun would still rise and set, yet it would climb from a different horizon, tracing an unfamiliar arc across the sky, while seasonal winds would arrive from new directions, bringing a sense of rain or dust at times we did not expect. In these ways, the passage of time itself would feel subtly altered, as if the universe had turned one of its great gears the other way. And in the next part of our exploration, we will follow that feeling further into how societies, cultures, and our shared sense of history adapt when the planet's rotation and the stories we tell about it are reversed. If we follow that feeling down into a single, ordinary day, the vast mechanics of the universe begin to touch something as small and familiar as an alarm clock and a bedroom window. Join us as we embark on a journey through a quiet morning on this backwards Earth, where the same stars and planets move overhead, yet the script of the sky has been gently rewritten. We can imagine waking before dawn in a modest home at mid-latitudes and noticing first not the clock, but the glow on the wrong horizon. The sun, the same main sequence star at the heart of our solar system, now rises in the west, lifting behind distant hills or city buildings that, in our world, never see first light. Shadows that once stretched toward the west now slide slowly eastward across the room, tracing the opposite path along the floor and wall, so that the familiar choreography of morning feels reversed, even though the flow of energy from the sun has not changed at all. Stepping outside, we would find the air itself telling a new story. The prevailing winds that, on our present Earth, tend to arrive from one direction, shaped by the Coriolis effect and the planet's eastward spin, now come from another, so that a person who has grown up here learns to expect a cool afternoon breeze from what we would call the opposite quarter of the sky, from tiny ripples on a pond to the steady drift of clouds. Everything that responds to rotation and gravity carries this subtle signature, a testament to the dynamic and transformative processes of the cosmos expressed on a human scale. As the year unfolds, the deeper rhythm of seasons still follows the same orbital rules, because the tilt of the axis and the path around the sun remain unchanged. Summer and winter still trade places as our hemisphere leans toward and away from our star, and the length of days still waxes and wanes in a pattern that would be entirely recognizable. Yet the timing and intensity of seasonal rains, monsoons, and storms are shifted by the reversed winds and ocean currents, so that regions that are dry in our world may, in these ways, become green and humid, while other coasts wait for storms that now form and travel along different routes. Over time, people on this backwards Earth come to treat these patterns as we treat ours. Children learn that storms usually arrive from a particular direction in the late afternoon, that the first cool winds of autumn feel a certain way on the skin, that the sun's path across the sky and the slow turning of galaxies at night are simply how life as we know it must be. The cues that would seem strange to us anchor their memories and stories. And yet, when we step back from this imagined day and look again at the whole planet turning the other way, we are reminded that our own familiar climate and sky are not inevitable, but contingent outcomes of one particular spin, one particular history of formation and motion. The winds we take for granted, the timing of rains and harvests, even the way light moves through a room at sunrise, all depend on that quiet rotation. In the next part of our exploration, we will leave this single day and follow those consequences outward into how entire civilizations, technologies, and futures might diverge when the planet beneath our feet rewrites the direction of its turning. We have watched a single day unravel under a reversed rotation, and now we can widen our view to the entire planet to see what this thought experiment truly reveals about the world we inhabit. The universe is a massive place filled with countless wonders of the cosmos. Yet even here on Earth, a simple change in direction can remake almost everything we find familiar. In climate models where Earth spins backwards, the basic ingredients remain the same sun, the same distance, the same continents and oceans, and the same physical laws of gravity and fluid motion. Yet the patterns that emerge are profoundly different. Trade winds that now blow from east to west would reverse, major jet streams would reorganize, and storm systems would curl in the opposite direction, reshaping the tracks of hurricanes and mid-latitude cyclones. Ocean currents, driven in part by those winds, would follow suit, with highways of heat like the Gulf Stream weakening, shifting, or even flowing the other way. From tiny eddies in the atmosphere to entire climate zones, the planet responds as a single, coupled system. The atmosphere, the oceans, the solid Earth, and the biosphere are all intertwined, so that a change in rotation, a deep property of planetary motion, cascades into new monsoon patterns, altered upwelling zones, and reorganized regions of rainfall and drought. In these ways, the retrograde Earth in our models is not a completely alien world, but it is recognizably rearranged, a testament to the dynamic and transformative processes of the cosmos acting on a familiar template. One striking outcome is that deserts and rainforests trade places. The Sahara, which today is one of the largest hot deserts on our planet, tends to become greener and more tropical in many simulations, while parts of the Americas, currently home to rich forests and fertile plains, dry into extensive arid belts. The great equatorial rainforests, the mid-latitude storm tracks, and the subtropical high-pressure zones we learn about in school are not inevitable features of Earth. They are the long-term results of our particular spin, our present continental arrangement, and billions of years of climate evolution. This realization can invite a quiet humility. The conditions that support life as we know it, from coral reefs nourished by present-day currents to agricultural regions timed to today's wind and rain patterns, are only one configuration among many that physics would allow. A backwards Earth in the models is still broadly habitable, still capable of sustaining complex ecosystems, but the map of opportunity and challenge for living things would be redrawn. Join us as we embark on a journey from this reimagined Earth to an even wider perspective, where our planet's rotation becomes just one example among many. Around us within our solar system, other planets spin at different speeds, with different tilts and even different directions, offering natural experiments in how rotation sculpts worlds. In the next section, we will place Earth's eastward turn alongside the varied rotations of our planetary neighbors, and see how our familiar day is only one possibility in a diverse family of spinning worlds. The universe is a massive place filled with countless wonders and mysteries, and even something as familiar as a spinning planet turns out to be part of a much larger pattern of motion. When we look beyond Earth and out across our solar system, we find that every world turns, yet each does so with its own rhythm, its own tilt, and its own history written into the direction and speed of its spin. Most of the planets, like Mars and Jupiter, rotate in the same general direction as Earth, an eastward or prograde, spin inherited from the original rotation of the protoplanetary cloud from which the solar system formed. Mars, a small rocky planet with a thin atmosphere, has a day length remarkably close to ours, only about 40 minutes longer, and an axial tilt of roughly 25 degrees, so its seasons and the march of sunlight across its surface feel strangely familiar in our models. Jupiter, by contrast, is a giant of gas and storms, spinning once in just under 10 hours, so its equator races through space at tremendous speed, a testament to the dynamic and transformative processes of the cosmos. Then we come to Venus, often called Earth's sister in size and composition, yet profoundly different in the way it turns. Venus rotates very slowly and in a retrograde direction, meaning it spins opposite to Earth and most other planets, so that if we could stand on its dense, cloud-covered surface, the sun would appear to rise in the west and set in the east. Its day, one full rotation, lasts about 243 Earth days, while its year, one orbit around the sun, is only about 225 Earth days. So a Venusian day is longer than its year, and the slow, backward spin reshapes how heat is distributed, how winds flow, and how the sky would change from one horizon to the other. Uranus offers another striking example with an axial tilt of about 98 degrees, so extreme that the planet effectively rolls on its side as it orbits the sun. One pole can face the sun almost directly for years, bathing that hemisphere in continuous light, while the opposite hemisphere sits in long darkness. And then the situation slowly reverses, creating seasons unlike anything on Earth. In these ways, Uranus shows us how gravity, collisions, and internal structure can combine to produce unusual patterns of illumination and climate. These diverse rotations, from Mars's near-Earth rhythm to Jupiter's rapid spin, from Venus's retrograde day to Uranus's sideways roll, reveal that impacts, tidal forces, and formation histories can push planets into a wide variety of spin states. Our own eastward rotating Earth, with its 24-hour day and moderate tilt that supports life as we know it, is only one outcome among many possible configurations allowed by physics. Join us as we embark on a journey into a hypothetical scenario where Earth's spin is reversed, and we explore how skies, climates, and oceans might change if our world had taken a different rotational path among the wonders of the cosmos. If Earth's familiar, orderly spin is only one option allowed by physics, then it helps to look at a nearby world where that option was not chosen. Venus, Earth's so-called sister planet in size and basic composition, offers us a striking example of how differently a planet's rotation, atmosphere, and surface conditions can evolve under the same overarching laws of the universe. Venus is almost the same size as Earth, yet it turns so slowly and in such an unusual direction that its day becomes one of the most extreme in the solar system. While our planet spins eastward once every 24 hours, Venus rotates backwards, or retrograde, taking about 243 Earth days to complete a single turn, and its thick, swirling atmosphere whips around the planet in only a few days, creating super-rotating winds that far outpace the surface beneath. From tiny particles of volcanic haze to the global cloud deck of sulfuric acid, everything on Venus seems to move in a way that reminds us how diverse planets can be. At the surface, this slow, backwards rotation is paired with an atmosphere so dense and hot that it crushes and bakes landers in a matter of hours, with pressures over 90 times those on Earth and temperatures hot enough to melt lead. Where Earth's rotation helps drive a complex but relatively gentle circulation that supports life as we know it, Venus's combination of retrograde spin, minimal day-night temperature contrast, and greenhouse-trapping carbon dioxide has produced a world of near-uniform searing heat, a testament to the dynamic and transformative processes of the cosmos. To understand how Venus ended up spinning this way, scientists have proposed several leading hypotheses, each tied to the early, chaotic history of the solar system. One idea suggests that a giant impact, perhaps comparable in scale to the collision that helped form our moon, struck the young Venus and altered its rotation so profoundly that it eventually settled into a backward spin. Another possibility emphasizes tidal interactions with the Sun, where solar gravity and atmospheric tides, raised in the dense Venusian air, gradually drained rotational energy and nudged the planet into a slow, retrograde state over hundreds of millions of years. Modeling this evolution is complex, because a planet's rotation is not determined by a single factor, but by a network of influences. Internal structure, including a liquid or solid core, affects how momentum is stored and exchanged. Atmospheric tides, especially in a thick atmosphere like that of Venus, can either speed up or slow down rotation. And the early solar system, filled with colliding protoplanets and migrating bodies, provided a constantly shifting gravitational environment. In these ways, the final spin of a planet emerges from countless interactions, rather than from a simple, predetermined rule. By studying Venus and other unusual rotators, such as Uranus with its extreme axial tilt, and some exoplanets that may be locked in slow, tidal dances with their stars, we gain valuable tests for our theories of planetary formation and long-term evolution. Join us as we embark on a journey through these case studies, because each strange rotation helps us refine our understanding of how planets across the galaxies acquire and transform their spins over billions of years. And if rotation can be flipped, braked, or reshaped so dramatically over deep time, we are left with a quiet but profound question. What might the distant future hold for Earth's own spin, for the length of our days, and for the rhythms that anchor our experience of time among the wonders of the cosmos? The universe is a massive place filled with countless wonders and mysteries, yet some of the most quietly profound changes unfold right beneath our feet in the slow turning of our own planet. Join us as we embark on a journey not through distant galaxies this time, but through the deep future of Earth's rotation and the lengthening heartbeat of our days. We begin with a process already at work. Tidal braking, the gentle but persistent transfer of angular momentum from Earth's spin to the Moon's orbit. As Earth's oceans are pulled into tidal bulges by the Moon's gravity, friction with the seafloor and coastlines drags against our rotation, very slightly slowing it, while the Moon is nudged outward. Over hundreds of millions to billions of years, this interaction lengthens the day, adding milliseconds that accumulate into minutes and then hours across deep time, a testament to the dynamic and transformative processes of the cosmos. From the present 24-hour cycle to a far future Earth with much longer days, the consequences would ripple through the atmosphere and oceans. The Coriolis effect, which today helps shape trade winds, jet streams, and swirling storm systems, depends directly on how fast our planet spins. As that rotation slows, Coriolis forces weaken, large-scale winds shift, and the familiar patterns of currents such as the Gulf Stream and the Kuroshio would gradually reorganize. Even without reversing direction, a slower Earth would host different storm tracks, altered monsoons, and new climate zones, quietly reshaping where rainforests, grasslands, and deserts can thrive. In the most extreme theoretical limit, if time and stability were available far beyond the Sun's main sequence lifetime, tidal breaking could carry Earth toward tidal locking with the Moon. In such a state, one hemisphere would always face our companion, while the other would never see it rise, much as the Moon already keeps one face turned towards us. Days and nights would still be set by Earth's rotation relative to the Sun, but the dance between Earth and Moon would be frozen into a single, unchanging orientation, a strange new configuration for life as we know it. Here we can pause for a pattern interrupt, stepping back from equations and climate models to something more personal. Our thought experiment imagined an abrupt reversal, a world where the sun suddenly rises in the west and storms spin the other way, while the real universe offers slower, quieter shifts. Days lengthening by fractions of a second, currents and winds evolving over eons. In these ways, both the instant flip and the gradual drift invite us to reflect on change itself, on how even our most basic experiences of morning and night are part of an ongoing cosmic story. As we look ahead to even more distant possibilities for Earth's spin, we carry this perspective forward, asking what other transformations might await our rotating world among the wonders of the cosmos. The universe is a massive place, filled with countless wonders and mysteries. Yet sometimes the most revealing experiments do not leave our planet at all, but simply invite us to imagine it, turned a different way. In this mirrored Earth, where the sun rises in the west, and the great storm belts and ocean currents trace unfamiliar paths, we can still picture cities lit at night, fields under changing skies, and cultures learning to live within a new but steady rhythm. On a backward spinning world, generations would grow up treating those reversed patterns as normal, building myths around western dawns and designing navigation, calendars, and timekeeping around the altered sky. The trade winds, redirected by a flipped Coriolis effect, would carve different routes for sailing and flight, and societies would place their great ports and power grids where the reconfigured currents and jet streams deliver the most reliable energy and rain. In these ways, civilizations would adapt their technologies and their stories to match the climate their planet offers, just as we have adapted to ours. The key difference is that this hypothetical Earth is stable, a long-settled outcome of rotation, gravity, and the formation of continents and oceans. By contrast, our real Earth is now shifting rapidly, not because the planet has reversed its spin, but because we have altered the composition of the atmosphere. Greenhouse gas emissions are quietly reshaping wind patterns, storm tracks, and ocean currents that have supported agriculture, coastlines, and ecosystems for thousands of years, changing the background conditions that life, as we know it, has come to expect. This contrast highlights both the fragility and the resilience of living systems. over millions of years, forests, coral reefs, and human societies can adjust to a different baseline. Whether that baseline is set by an eastward or westward rotation, or by slightly different distances to the sun. Yet abrupt shifts compressed into decades strain that adaptive capacity, pushing species, cities, and entire regions to their limits as familiar rainfall, temperature, and ocean circulation patterns move faster than many can follow. Join us as we embark on a journey from this thought experiment back to our own responsibilities. Because while we cannot reach out and flip the direction of Earth's spin, we do influence the climate system with every choice that affects energy use, land, and the thin atmospheric shell surrounding our planet. Understanding how sensitive circulation, clouds, and ice are to relatively small changes reminds us that our actions are a testament to the dynamic and transformative processes of the cosmos playing out at human scales. As we prepare to leave this reversed world behind, we can ask which images stay with us most clearly. The sun rising over an unfamiliar ocean, storm spirals turning the other way, or new green belts where deserts once stood. In the closing moments of our journey, we will gather these images and insights and consider what they reveal about our own rotating world and about the futures still available to us beneath the turning sky. As we leave that imagined reverse world behind, we can let our thoughts drift back to where this journey began. With Earth, a small, bright sphere turning quietly in the dark, its continents and oceans carried eastward beneath the stars. Then, almost imperceptibly, we asked what would happen if that steady motion slowed, paused, and began to turn the other way, so that the same planet, under the same sun, became a mirrored version of the world we call home. From that single change in direction, we followed the cascade of consequences, from the vast scale of the atmosphere and oceans down to the view from a single window. We recalled that Earth's rotation, the simple fact that it spins once every 24 hours, divides light from darkness and gives us the rhythm of day and night, while the Coriolis effect born from that spin guides winds into great circulating bands, shapes trade winds and jet streams, and helps to organize the ocean currents that move heat around the globe. In these ways, rotation acts as a quiet architect of climate zones, tracing out deserts, rainforests, and temperate bands. By imagining the spin reversed, we watch those systems rearrange themselves. The sun, which now appears to rise in the east because Earth turns eastward at over 1,600 kilometers per hour at the equator, would instead seem to rise in the west and set in the east, and the familiar arc of star trails across the night sky would slowly sweep in the opposite direction. Large storms which owe their counterclockwise or clockwise spirals to the Coriolis effect would unwind and reform with the opposite twist, so that hurricanes and cyclones would rotate the wrong way, even as they still drew energy from warm oceans and towering clouds. We paused with some of the most striking images. A green Sahara, no longer a vast desert but a belt of forests and wetlands nourished by new wind and rain patterns. Altered monsoon paths that shift belts of rainfall from one continent to another, and great ocean highways such as the Gulf Stream, weakening or reversing, redirecting marine life and changing where fisheries thrive or collapse. Join us as we embark on a journey through memory here, noticing how each example is a testament to the dynamic and transformative processes of the cosmos, in which a small change in motion can ripple outward into new landscapes and new forms of life. Finally, we brought these global patterns back to the scale of a single life. In such a mirrored Earth, the weather outside your home, the timing of seasons, and even the cultural meaning of East and West would feel different. Yet for those born there, it would be normal, as natural as our own sky feels to us. From the apparent path of the sun that sets the cadence of daily routines, to navigation systems, maps, and stories that tie direction to memory and meaning, rotation would still quietly frame experience, just with its arrows reversed. The wonders of the cosmos include not only distant galaxies and stars, but also the subtle ways a planet's spin shapes life as we know it. As we move toward our closing reflections, we can let these images settle like slowly drifting clouds, allowing the mirrored Earth to fade while the insights remain. In the next moments, we will gently turn back to our own world and consider what this exercise in reversal reveals about the delicate balance that sustains us, and about the many possible futures still turning with our planet beneath the silent sky. As we let the mirrored Earth drift to the edges of our imagination, we can now hold two worlds gently in mind, suspended together against the dark canvas of the universe. Join us as we embark on a journey of comparison, where our familiar planet and its backward spinning twin turn side by side, each wrapped in swirling cloud, sculpted by gravity and illuminated by the same distant sun. On one side there is the Earth we know, the sun rising in the east, trade winds carrying moisture toward the equator, and ocean currents like the Gulf Stream ferrying warmth toward Europe, helping to soften winters and sustain life as we know it. On the other side, the retrograde Earth turns the opposite way, so the sun appears to rise in the west. The great storm systems spin in reversed spirals, and the major currents bend along unfamiliar paths, redistributing heat and rainfall to create green belts where deserts once stood, and arid zones where forests used to thrive. In these ways, the contrast can seem dramatic, yet both planets are governed by the same quiet rules. The equations that describe rotating fluids, the pull of gravity that shapes oceans and atmospheres, and the flow of energy from star to planet do not change. What differs are the starting conditions and the long, branching history that follows. A slightly altered spin, a different pattern of impacts early in formation, and the slow feedback of ice, cloud, and climate over billions of years are enough to repaint coastlines of habitability without ever breaking a single physical law. When we hold both Earths in view, our idea of what is normal begins to soften. The familiar pattern of winds and seasons becomes just one possibility among many that the cosmos could have written on a rocky world. From nearby exoplanets orbiting red dwarf stars to distant worlds in other galaxies, there may be planets that spin more slowly, tilt more steeply, or even roll sideways, each with its own shifting tapestries of cloud and ocean, each a testament to the dynamic and transformative processes of the cosmos. If observers exist on some of those distant planets, their everyday sky might be utterly unlike ours. Perhaps their stars rise in strange directions, or their constellations slide backward across the night, or their days stretch so long that a single sunrise marks an era. As we imagine waking beneath a westward sunrise on our backwards Earth, we can also imagine them looking up from alien continents, taking for granted patterns that would seem extraordinary to us. This dual vision invites a quieter question, one that will guide our final reflection. In a universe with so many possible spins, climates, and histories, what does it mean to be fully awake and present on this particular world, turning eastward through the night right now as the next rotation silently carries us on? In a universe with so many possible paths, from worlds that spin backwards to planets locked forever to their stars, we now return to the one place we actually stand. As we gently set aside the image of a reversed Earth, with its westward dawns and unfamiliar winds, we come back to the quiet certainty beneath our feet, our planet turning steadily eastward, carrying us toward the next sunrise, whether we notice it or not. The Earth, a modest rocky planet in our solar system, rotates once every 24 hours, defining the rhythm of day and night that structures life as we know it. From our perspective on the surface, this rotation makes the sun appear to rise in the east and set in the west, and it draws the familiar constellations in slow arcs across the sky. From Orion in winter evenings to the graceful band of the Milky Way on clear summer nights. From tiny particles in the air to massive oceans, everything is participating in this motion. We rarely feel this turning, yet its effects are all around us. The Coriolis effect, born from Earth's rotation, guides the broad sweep of trade winds and jet streams, shaping where storms form and where deserts stretch across continents. In these ways, a force we cannot touch directly becomes visible in the spiral of a hurricane, in the steady flow of ocean currents that carry heat and energy between the hemispheres, and even in the gentle patterns of clouds drifting past a city skyline. Knowing this, we can choose to meet our spinning world with a little more attention. We might rise early and watch the eastern horizon brighten, aware that we are rotating into the light, or sit quietly at sunset and feel ourselves turning away again, the stars slowly reclaiming the sky. We can notice the direction of the winds on a blustery day or, on a clear night, trace the paths of stars over an hour or two, seeing their circular trails as a direct imprint of Earth's rotation, a testament to the dynamic and transformative processes of the cosmos. Understanding the mechanics behind these scenes does not strip them of their beauty. Instead, it deepens it. When we learn how gravity holds our planet together, how rotation shapes our climate and weather, and how these same principles govern distant planets and galaxies, the view from a window or a quiet field becomes part of the larger wonders of the cosmos. A simple sunrise becomes linked to the formation of the solar system from a collapsing cloud, and to countless other worlds turning in their own ways. Join us as we embark on a journey that continues beyond this single thought experiment, carrying forward a soft, persistent curiosity. We can keep imagining other possible worlds with different spins and skies, while resting in the calm knowledge that our own world is turning reliably beneath us. As the Earth rotates eastward through the night, we remain passengers on a moving sphere, part of a vast dynamic cosmos, where even the direction of a planet's spin can tell a story, and where there is always more to wonder about, just beyond the next horizon. In this quiet moment, as we picture our planet gliding through space, we can allow ourselves one last gentle thought experiment. If we could pause the universe for an instant and choose between the Earth we know, spinning eastward with its familiar patterns of day and night, and an alternate Earth turning the other way, with reshaped climates, redirected winds, and a different history written under different skies, Which world would we ask to continue? And why? The Earth as it is has given rise to life as we know it, with its existing arrangement of oceans, deserts, forests, and ice, all sculpted over billions of years by rotation, gravity, and sunlight. A backwards spinning Earth, by contrast, would send trade winds and ocean currents along new paths, might turn some deserts into green belts and some fertile regions into dry plains, and would invite cultures to grow around different coasts, different storms, and different stars rising first on the horizon. When we imagine choosing between them, we are really weighing the comfort of the known against the pull of curiosity. In these ways, the question reaches beyond climate and geography into something more personal. We can ask ourselves how much we value familiarity, the inherited patterns of our own lives, and how much we are drawn toward diversity of experience, toward the idea of walking different shorelines, reading different constellations, and listening to different winds shaped by a different spin. Life, whether on this Earth or any other planet circling distant stars, survives by adapting, by finding new paths through changing conditions, and our cultures do the same as they respond to shifting environments and new possibilities. So this imagined choice between two Earths becomes a quiet symbol for a broader decision we face again and again. How we respond to change, to uncertainty, and to the many possible futures that physics allows, and human decisions select among. From small personal changes to planetary scale choices about energy, climate, and exploration of the solar system, we are always, in a sense, deciding how we wish our shared story to spin forward. Each option carries risks and opportunities, and our willingness to adapt is itself a testament to the dynamic and transformative processes of the cosmos that produced us. There is no need, though, to arrive at a final answer. We can simply hold the question lightly, letting it drift through our thoughts like a slow-moving cloud, as we rest in the awareness that we live on a rotating sphere whose very motion ties together mornings and evenings, memories and expectations. Join us as we embark on a journey, not outward this time, but inward, to notice how it feels to imagine other paths while remaining grounded on this one. As we let the image return of Earth turning silently in space, we can picture its thin blue atmosphere wrapped around rock and water, its continents passing in and out of sunlight, its night sides glowing with storms and cities. From tiny particles in its core to the galaxies that surround it, everything is in motion, and the direction of that motion is only one part of the story. Whichever way our planet spins, its rotation continues to knit together days and nights, seasons and cycles, and the unfolding stories of everyone who has ever looked up at the sky and wondered about their place in the universe.